Hello, we'll meet again. We continue our meeting today with chapter 5 of Form 4, the very last chapter of Form 4 on light. Okay, so before we answer the problems, let's go over some important main ideas or main point in the chapter. Okay, so first we look at law of reflection. Okay, so this law of reflection, it says that the angle of incident must equal to the angle of reflection. Okay, this is the first thing in the law of reflection. Okay, the second thing in the law is the incident ray. Okay, this incident ray and the reflected ray and then the normal, all these rays must be in the same plane. And I put a note here, right? So make sure when you measure the angle must be measured with respect to normal. Meaning if this is your incident ray, then the angle must be measured from this ray to the normal. Okay, so this is your incident ray angle. The same thing goes to the reflected ray. The angle would be from the reflected the reflected ray to our normal. Okay, that's how we measure the angle. Okay, it always with respect to the normal. Okay, so what are the characteristics of the image formed by a plane mirror? Okay, or any mirrors, all right? So the characteristics are they are of the same size, the size are the same. It's virtual meaning you cannot form the image on the screen, and then it is laterally inverted, or in Bahasa Melayu it is songsang sisi, upright, and the object distance must equal to the image distance. All right. So these are the characteristics of the image formed by a plane mirror. And then how do we draw a ray diagram for plane mirror? Okay, so to draw a plane diagram, first, okay, you check first where is the object. Okay, our object is at point A here. So what we do next is we measure the distance from the object perpendicular to the mirror. Okay, so we measure this distance first. Let's say that this distance is 5 centimeter. Okay, so once you have measured the distance, what you do next is you measured, okay, the same distance 5 centimeter beyond the mirror. Okay, so here is also 5 centimeter because I know that the object distance, which is AB, and the image distance BC, they must be the same. We have covered it just now. Okay, so I know the image will be here. So what do I do next is I draw two lines, okay, two lines, straight lines towards the eyes, okay, two straight lines toward the eyes. Okay, so that is step number 3 that I have written on the line there. Okay, so what is next? Okay, so I know that this must be my reflected ray. So where is my incident ray? So from this point on the mirror, I draw that line straight to the object. Okay, same thing goes to this line down here, straight to the object. And you can check your work, okay, by drawing the normal. Step number 5 here, I draw the normal, and you can measure the angle of incident and the angle of reflection. Okay, the value must be the same. Okay, if you measure the angle of incident here, let's say this is I2, and then here the angle of reflection, which is R2, these two angles must be the same. Okay, and finally, you must draw the arrow to denote the directions of the light propagation. So light travel from the object to the eyes. Okay, not vice versa. Okay, unless you are X-Men, then your eyes can emit light. Oh, Okay, so the light must come from the object, okay, and then it will be reflected to our eyes. That's how we draw ray diagram for plane mirror. Okay, next. Just now we work on plane mirror, okay, and now we look at curved mirror. So we have two types of curved mirrors, concave mirrors and convex mirrors. Okay, so how do we draw the ray diagram? So for a concave mirror, okay, a light parallel to our principal axis. Okay, here is our principal axis. Or in Bahasa Melayu it is called as paksi utama. Okay, the light which is parallel to this principal axis, it will be converged, okay, to the focal point here. Okay, so we can use our law of reflection. If I draw my tangent line here, okay, and then I draw my normal, you can see that the incident ray here is being reflected uh, according to the law of reflection, okay, whereby here is my I, okay, and then here is my R, angle of reflection. And that's why when I have a parallel ray to the principal axis, okay, that light ray will be reflected towards our focal point. Okay, that is step number one. So for a convex mirror, we do the same thing. Okay, I draw a line parallel to my principal axis, but then what happened? So if I draw my tangent line here, okay, and then I draw my normal line, you can see that the angle of incidence, okay, is being reflected according to the law of reflection, whereby my angle of incidence equals to my angle of reflection. Okay, but this the ray being reflected, there must be a reference point. Okay, here it's being reflected towards the focal point. Here the ray is being reflected away from where? So it must be away from the focal point. All right, so that's how we draw the first line for concave mirror and also a convex mirror. Okay, now we go to step number 2. In step number 2 here, okay, or line number 2, I draw a line that is going through the focal point. So what happened? It will comes out straight. Okay, it's just like this one here, right? Except that now our direction is reversed, right? Okay, so for here, the same thing. If I draw a line, okay, and it seems to me that this line, it is going through this focal point, so the reflected ray, it will be parallel to the principal axis. That is step number 2 for concave and for convex mirror. Basically the same steps. You need to apply your law of reflection to see where the reflected ray will be. And lastly, the third step. Okay, now this line, it go through this point C, the center of curvature. So if I have a line of or a ray that go through this point C, it will be reflected by the mirror, okay, forming the same line with the incident ray. It will be on the same line. Okay, that's why you see my arrow. Okay, here is my arrow for my incident ray, and here is the arrow for my reflected ray. Okay, so for a convex mirror, you see here, I draw a line here. If I prolong the line, it will hit my point C here. So what happened? It will be reflected on the same line. Okay, so you can see my arrow going up, and this arrow going down. Here is my incident ray, and this arrow is for my reflected ray. So these are the 3 steps in drawing ray diagram for curved mirror. Even though there are 3 steps, you only need 2 steps. Okay. Upon drawing these 2 steps, you need to find where the lines intersect. So the point where the line intersect is where the image will be formed. Okay. So one thing about this curved mirror that you need to know, okay, for both convex and also for a concave mirror, PC equal to 2PF or 2CF. In other words, we are saying that this F is the midpoint. Okay, so this point F is the midpoint between C and F, meaning the distance between FC and FP, they are the same. Okay, so if we use our mathematical term, this CP is actually we call as the radius. Okay, in mathematics we call as radius. But in physics we call this distance C to P, we call it as the center of curvature. Whereby this point P here we call it as the pole of the mirror. Okay, can you follow? Alright, now just to make things easier for you, okay, you see this mirror here? If I complete the circle of this mirror, okay, my C and F is in the circle, okay. If I do the same thing for this convex mirror, alright, my F and C is also in the circle. So if I'm to draw the line for a concave or for a convex mirror, okay, use the F and the C in the circle. Okay, use the F and the C in the circle. Do not use the F and the C outside the circle. Alright. Okay, so we go to the next one. Okay, we have talked about mirrors. So now we move to lenses. Alright, first, how do we determine the focal length of a convex lens? Okay, convex in Bahasa Melayu is cembung. Okay, this is our kanta cembung. Okay, to determine the focal length of a convex lens, right? First, we use an object, a distant object, for example, a tree outside the lab, okay, as our object, and then we let the light to go through our lens, and then we adjust the screen until we get the sharpest image formed on the screen. Okay, as you can see here, the image will be diminished, it will become smaller, and it is upside down. Right? It can be formed on the screen, then this image must be real. Okay, so as I said just now, we adjust the screen until we get the sharpest image formed on the screen, and then we measure the distance between the lens and the screen. So this distance is our focal length. Okay, so this distance is our focal length. Focal length, jarak fokus. Simple, right? So if I draw a ray diagram for this, you will get something like this. Okay, I purposely draw this line in red because I do know that anything that go through the center of the optic, okay, the optical center, that line will not be deviated, right? It will just go straight. You can see here this red line here, it goes through the center of the lens, okay, the optical center. It will just go straight. It will not be deviated, okay, it will not be deflected. Okay, let's move back to this picture here. So I have parallel rays coming towards my lens. So what happened? It will be converged to a point here. Okay, and what is this point? This point is our focal point. So the distance from here, okay, to here is our focal length. Okay, but what if the lines are not parallel? So no problem, So what I do first is I draw this line going through the center of the optic. It will just go straight, and then suppose here is my focal point, so I draw a line going straight down, okay, and then all these lines here, the slanted line, it will be converged to a point on the line here, okay, this line here, okay, you will intersect the red line at this point. So again, the distance from here to here is our focal length. All right, so that is how we determine the focal length of a convex lens. Actually, we have other method as well, but this is the easiest one that we can do in the lab. Okay, next is how do we draw ray diagram for lenses. So just like mirrors just now, we have convex and also concave. Okay, before we move on, remember that when light travels from dense area to a less dense area, the light will be diverted away, okay, or deflected away from the normal. Okay, so I repeat, when light travels from more dense to less dense, the light will be refracted away from the normal. If the light travels from less dense to a more dense medium, then the light will be refracted towards the normal. Okay, that concept, you must grasp it pretty well. Alright, so now, how do we draw ray diagram for lenses? So just like mirrors, we need to draw lines. Okay, there are 3 lines just now, but we need to draw only 2 lines and then find where the 2 lines intersect each other. Okay, so let's go to convex lens. Okay, so you see here the line in red here, it goes straight and it hit my optical center. So what happened? It will go straight. Same thing goes to my concave lens. Okay, is it red? Almost red, but it's almost purple as well. So if I draw a line, okay, and it hit my optical center, it will just go straight. Okay, so that is line number 1. Okay, let's say it's purple lah. Yeah. Okay, now line number 2. Okay, I draw a line parallel to my principal axis. Okay, draw a line parallel to my principal axis. And what happened after it hit this center line of the optic? It will be converged to my focal point. However, for a concave lens, okay, the line parallel to my principal axis, it will be diverged from the focal point. Okay, let's see how this thing works. Okay, suppose here is my convex mirror, right? And I have a light going like this. Okay, so what do? Is I draw my tangent line as usual because I have a curve. So I draw my tangent line and then I draw my normal, right? By right, this line is supposed to go straight, correct? But since I am moving from a more dense, okay, more dense is in the mirror and outside here is less dense. So what happened? Okay, what happened is this light ray, it will be refracted away from the normal. Okay, it will be refracted away from the normal. So if I draw my principal axis down here, so it will intersect at my focal point. Okay, now if I draw another lens, okay, there is a concave lens. It's something like this, right? Okay, Now, suppose I have a light ray coming like this. Okay, so what I do next is I draw my tangent line, and then I draw my normal. So by right is supposed to go straight, but since the light is moving from more dense to less dense, it will be refracted away from the normal. Okay, here is our normal just now. So the light will be refracted away from the normal. So if I prolong or elongate this line here, and suppose here is my principal axis, so this point here is my focal point. Okay, so that's what is happening here when we draw line number 2 here. And then the third line that you can draw is just like the mirrors just now, we use the F in front, right? So if I draw a line going through my focal point, okay, so what happened? It will go straight. Okay, same thing goes to here. If I look at this line in red, okay, this line here, if I draw this line and I can see that it is hitting my focal point, so what happened? It will go straight, parallel to my principal axis. So just like mirrors just now, you don't need to draw all these 3 lines, you only need to draw 2 and then find where the 2 lines intersect each other, and that point of intersection is where the image will be. For example here, okay, if we look at this purple line and this blue line, it intersect at this point. So since I'm using the head of the arrow, so the head of the arrow must be drawn here, and then the foot must be on my principal axis. Okay, so that is ray diagram for lenses. Okay, so I have notes down here. When stating the characteristics of the image form, all these 3, okay, must be written. Okay, you must mention whether the image is virtual or real, upright or inverted, and then the size is same size or magnified or diminished. Okay, so remember, virtual meaning the image cannot be formed on the screen. Real image are images that you can form on the screen. Okay, so there are a few formulas really relating to lenses. Okay, so but first we look at the sign convention. So for sign convention, almost all are positive, okay, except for the image distance for convex if it's virtual, okay. And then for concave lens, the focal length would be negative and the image distance would be negative. Okay, can you follow? So if we look at this convex lens, virtual, okay, it only happens, suppose here is F, here is my lens. If I have object here, okay, if I draw, okay, I will have something, image will be formed behind here. So if I measure my image from the lens towards the object. So I'm going to the left. Okay, so negative value. Okay, so same thing goes to our concave lens. If I go up, okay, if I go up, you see here is my image. See my lens. So to measure the image distance, we measure from the image, sorry, from the lens to the image. So I'm going to the left. Okay, but to measure the object distance, we measure from object to the lens. Okay, so we always go from left to right. Okay, you see here, if I want to measure my image distance, I measure from the lens, okay, going to the right, to the image, okay, going to the image. So I'm going to the right, so I will have a positive value. All right, so that's how we can memorize this negative and the positive sign convention. Okay. All right. So it's good if you can memorize this. Actually, you need to know about this sign convention. Next, we go to magnification. Okay, to calculate magnification, it is always image divided by object. You can use the size, you can use the distance, okay, but it's always image divided by object. For telescope, you can determine the magnification by dividing FO with FE. But for microscope, okay, you multiply each magnifications, okay. So MO here is the magnification by the objective lens. ME here is the magnification by the eyepiece lens. So you multiply these two, you will get the magnifications of a microscope, okay. All right. And then we have this formula, 1 over f equal 1 over u plus 1 over v. Okay, f is our focal length, u is our object distance, and then v is our image distance. All right, so here is the apparatus if we want to study the relationship between u, v, and f. All right. And then lens power. Okay, lens power is 1 over focal length. But be careful, the focal length, it must be in meter. You cannot use centimeter in determining the power. Okay, it must be in meter. Okay, and the unit for power for lens is diopter. Okay, which is equivalent to, if I use this formula, that will be meter to the power of -1, right? So that is our diopter. Okay, and finally for lens here, I summarize. If the lens thickness increases, the focal length will decrease. Okay, when the focal length decreases, then the lens power will increase. So this one here, it comes from this formula up here. When the focal length decrease, then the lens power, the power will definitely increase. Okay, so we go to the next part, devices using lenses. So we have a few devices. So first we look at compound microscope. So for microscope, we are using two convex lens. Okay, the lens which is closer to the object is called as the objective lens, and the eyepiece is the one closer to our eye. All right, so what do I need to know about designing a compound microscope other than using two convex lenses? Okay, so first is the focal length of objective lens. Okay, FO, it must be less than FE. That is point number one that I need to know. Okay, my FO here must be less than my FE. Okay, FE is the focal length of the eyepiece lens. And then the distance between the two lenses, the objective lens and the eyepiece, the distance must be greater than the summations of these two focal lengths. Okay, it must be greater. So that's how we built a simple compound microscope using two lenses, two convex lenses, whereby the focal length of the objective lens must be less than the focal length of the eyepiece lens. All right. Now, contrast this to a telescope. Okay, so here is the design, the layout for telescope. Again, we are using two convex lenses, but there is a bit different here. All right, now our objective focal length is greater than FE. Right? Actually, this is common sense because we use telescope to see what? To see the stars, to see the moon, right? So the objects are very, very far away. So definitely my focal length for objective lens must be greater than the focal length for eyepiece. So that's point number one. And point number two is the distance between the two lenses. the distance between the two lenses must equal to the summations of the two focal lengths. That is point number 2. Okay, so that's how we build microscope and telescope. So if I have microscope, then FO must be less than FE, because we put the object just beneath the microscope, very close to the lens, right? So this is for microscope. But for a telescope, reverse. Okay, FO must be greater than FE. All right, and then we have another one, magnifying glass. Okay, it's very simple. We just use a convex lens and then we put the object here. So notice that my object distance, okay, it must be less than my focal length. Okay, from here to here is my focal length. From here, from this object to my lens, that is my object length. Okay, or the object distance. Okay, so my U must be less than F. Then you will get a magnified image, and this image is virtual. Okay, before I forgot, mirrors and also lenses, when it comes to characteristic of the image, they always contradict each other. Okay, when mirrors say it's virtual, lens will say it's real. Like in this case, I have virtual. Okay, if the image of the object of a lens, okay, is on the same side with the object, then this image must be virtual. But if the image can pass through, it is here on the other side, then that image must be real. Okay, that is for lenses, but mirrors will say vice versa. Okay, remember, when convex say real, then mirrors will say virtual. Okay, next we look at smartphone and CCTV. Okay, it's just like our camera lubang jarum, which you don't learn in your physics. Okay, uh, just follow the line. Okay, if this is the head, then the head would be down here. I just follow my line here. Is the foot, so I just follow, so the foot must be here. So I can see that the image form inverted, right? It's upside down and then diminish, right? Okay, so that is for smartphone and CCTV. Okay, next in the topic we also talk about refraction. So refraction happens when light travels from one medium to another medium of different density. Okay, so different density, so what happened? The speed will change. Okay, so when the speed change, then the directions also change. Okay, so I add here direction also changes. Okay, so when light entering more dense medium, so the light will bend towards normal, so speed will be decreased. When the light enter less dense medium, okay, from more dense to less dense, so the light will bend away from normal. So here I'm using the term bend away or bend towards. Okay, so this bending here, you can change this word with refract. Okay, DBS or pembiasan, away from the normal if it entering less dense medium. Okay, so entering less dense medium, the speed will increases. Okay, the speed will increase. Okay, next we look at refractive index. So this refractive index, as I have told you before, the value of this refractive index must always be greater than 1. Okay, it cannot be less than 1. If you get a value less than 1, then you take the reciprocal. Okay, So talking about refractive index, we have one law, which is the Snell law. Okay, Snell's law simply is the ratio of sin I to sin R is a constant. That is what stated by Snell's law. Okay, so it says that sin I, the sine of the incident angle divided by the sine of the reflected angle, this must be a constant. Okay, follow. Okay, now we can also find the refractive index if we know the critical angle. Okay, so if you know the critical angle, then you can use this formula 1 over sin C, right? Other formula for refractive index would be the velocity in vacuum divided by the velocity in a medium, for example, water. Or real depth divided by apparent depth. Okay, and remember that the depth is measured from the surface to the point of interest, not from bottom up, but from up going down. That is depth, right? Okay, so here are examples of refractions or and ray diagram. Okay, you see here I have a diver. Okay, and this is the instructor. The instructor will see the image of the diver up here. So how do we draw this? Okay, it's very simple. You draw a line going straight up. Okay, and then this line, it must straight to the observer, the instructor. Okay, just draw it straight. So here is where this line here intersect with the surface of the water. So I draw a normal line, and I do know that, okay, if I work reverse from less than to more dense, right, from air to water, okay, so what happens if I enter more dense? It will be refracted towards the normal. So that's why I have a bend line here. It's going towards the normal. Okay, so from this line I will go straight, I will draw straight to the diver here, and then lastly I will draw this line just to show how the light propagates or how the light travels. All right, follow. Okay, that's what the instructor see, and this is what the the diver see the instructor. Okay, the diver will see the image of the instructor up here, right? Okay, so same thing goes to this one here. Okay, you see here this line. Okay, first is you have to draw a line straight. Okay, draw a line straight, and then from this point I draw two lines going straight to the eye. And then I draw the normal line here, and I do know that the light will be refracted towards the normal. Okay, we will see this again in the problem that I have given you. Okay, next, total internal reflection. Okay, observe the differences, the main difference between these three diagrams. Okay, so in the first picture, my I is less than C. Okay, what is C? Okay, C is our critical angle. So if I, the incident angle, is less than my critical angle, so I will see my refracted ray. Okay, the light will emerge from the medium. Okay, like in this case the light travel from glass to air, so from more dense to less dense. So what happened? It will be refracted away from normal. It's supposed to go straight like this, correct? But it will be refracted away from normal. Okay, but if my angle incident here equal to my critical angle, so what happened? Okay, what happened is I will have the light being refracted parallel to the surface here, meaning to say that my angle of reflection is 90 degree. Okay, if you take sine of 90, that will be 1, right? So that's why up here just now you can see to find or to calculate my refractive index, the formula is n equal to 1 over sin c. Okay, now what happens if my angle of incidence is greater than my critical angle? I don't have anything coming out from the glass, so there is no refraction. Okay, but the light will be reflected inside the glass. Okay, so here I have no refraction, but I have reflection. Okay, so meaning to say this angle of incidence and this angle of reflection, it obey the law of reflection, whereby I must equals to R. So if this happen, then we say we have total internal reflection. Okay, pantulan dalam penuh. So for a total internal reflection to occur, you must have these two. First, light must travel from more dense to less dense medium. And two, the angle of incidence must be greater than the critical angle. Okay, so these two are the condition for total internal reflection to happen. Okay, next we look at mirage. Sometime in a very hot day, okay, on a very hot day, you can see pool of water on the ground, but as you approaching it, there's nothing there. So what is happening? All right, so the light travel from the clouds towards the eyes of the observer. So as the light ray going down, it is entering, okay, it's entering from a cooler air to a hotter air. Okay, so at the surface of the earth, the air is hot. So when the air is hot, so the distance between the particles is much further. Okay, so when the distance is further, so what happened to the density? So the density will become less. All right, so remember what we said just now. If light enters less dense medium, okay, from a more dense to a less dense medium, the light will be refracted away from normal. So if you look at my line here, okay, for example here, okay, it's supposed to go straight like this, but it will be refracted away from normal until this point here. So what happened at this point? Okay, at this point now, my angle of incidence is greater than my critical angle. So I will have my total internal reflection. So it will go up and straight to the observer's eye. Okay, so the density decreases. All right, so the ray will be gradually refracted more and more away from normal. So meaning to say that the ray is now moving towards the horizontal, okay, until the angle of incidence become greater and greater until it become greater than the critical angle. So at point Y, okay, the angle of incidence is greater than critical angle, then we have total internal reflection. Then you will see the image of the sky appears on the road as a pool of water. All right. So that's about it regarding the important ideas in light. Okay, so I stop here first before we continue with the problem solving.